We've got a real problem with math education right now. Basically, no one's very happy. Those learning it think it's disconnected, uninteresting, and hard. Those trying to employ them think they don't know enough. Governments realize that it's a big deal for our economies, but don't know how to fix it. And teachers are also frustrated. Yet math is more important to the world than any point in human history. So at one end, we've got falling interest in education in math, and at the other end, we've got a more mathematical world, a more quantitative world than we ever have had. So what's the problem? Why has this chasm opened up, and what can we do to fix it? Well, actually, I think the answer is staring us right in the face. Use computers. I believe that correctly using computers is the silver bullet for making math education work. So to explain that, let me first talk a bit about what math looks like in the real world and what it looks like in education. See, in the real world, math isn't necessarily done by mathematicians. It's done by geologists, engineers, biologists, all sorts of different people, modeling and simulation. It's actually very popular. But in education, it looks very different. Dumbed-down problems, lots of calculating, mostly by hand. Lots of things that seem simple and not difficult, like in the real world.
I'm here to tell you that the way our textbooks, particularly math-adopted textbooks, teach math reasoning and patient problem solving, it's functionally equivalent to turning on 2.5 Men and calling it a day.
Well, I think it's about 4 steps, roughly speaking. Starting with posing the right question. What is it that we want to ask? What is it we're trying to find out here? And this is the thing most screwed up in the outside world, beyond virtually any other part of doing math. People ask the wrong question, and surprisingly enough, they get the wrong answer, for that reason, if not for others. So the next thing is take that problem and turn it from a real-world problem into a sort of math problem. That's stage 2. Once you've done that, then there's the computation step. Turn it from that into some answer in a mathematical form. And of course, math's very powerful at doing that. And then finally, turn it back to the real world. Did it answer the question? And also verify it, crucial step. Now here's the crazy thing right now. In math education, we're spending about perhaps 80% of the time teaching people to do step 3 by hand. Yet that's the one step computers can do better than any human after years of practice. Instead, we ought to be using computers to do step 3, and using the students to spend much more effort on learning how to do steps 1, 2, and 4, conceptualizing problems, applying them, getting the teacher to run them through how to do that. See, crucial point here, math is not equal to calculating. Math is a much broader subject than calculating.
Here's a really cool problem. I like this. It's about defining steepness and slope using a ski lift. But what you have here is actually 4 separate layers. And I'm curious which of you can see the 4 separate layers, and particularly how, when they're compressed together and presented to the student all at once, how that creates this impatient problem solving. I'll define them here. You have the visual, okay? You also have the mathematical structure, talking about grids, measurements, labels, points, axes, that sort of thing. You have sub-steps, which all lead to what we really want to talk about, which section is the steepest. So I hope you can see, I really hope you can see how what we're doing here is taking a compelling question, a compelling answer, but we're paving a smooth, straight path from one to the other and congratulating our students for how well they can step over the small cracks in the way. That's all we're doing here. I start with the visual, and I immediately ask the question, which section is the steepest? And this starts conversation because the visual is created in such a way where you can defend 2 answers. So we get people arguing against each other, friend versus friend, in pairs, journaling, whatever. And then eventually we realize it's getting annoying to talk about the skier in the lower left-hand side of the screen, or the skier just above the midline. And we realize how great would it be if we just had some A, B, C, and D labels to talk about them more easily. And then as we start to define, like, what does steepness mean, we realize it'd be nice to have some measurements to really narrow it down specifically what that means. And then, and only then, we throw down that mathematical structure. The math serves the conversation doesn't serve the math. And at that point, I'll put it to you that 9 out of 10 classes are good to go on the whole slope steepness thing. But if you need to, your students can then develop those sub-steps together. Do you guys see how this right here compared to that, which one creates that patient problem solving, that math reasoning? It's been obvious in my practice. to me. So 90% of what I do with my 5 hours of prep time per week is to take fairly compelling elements of problems like this from my textbook and rebuild them in a way that supports math reasoning and patient problem solving. And here's how it works. I like this question. It's about a water tank. The question is, how long will it take you to fill it up, okay? First things first, we eliminate all the sub-steps. Students have to develop those. They have to formulate those. And then notice that all the information written on there is stuff you'll need. None of it's a distractor, so we lose that. Students need to decide, all right, well, does the height matter? Does the side length matter? Does the color of the valve matter? What matters here? It's such an underrepresented question in math curriculum. So now we have a water tank. How long will it take you to fill it up? And that's it. And because this is the 21st century, and we would love to talk about the real world on its own terms, not in terms of line art or clip art that you so often see in textbooks, we go out and we take a picture of it. So now we have the real deal. How long will it take it to fill it up? And then even better is we take a video of someone filling it up. And it's filling up slowly, agonizingly slowly. It's tedious. Students are looking at their watches, rolling their eyes, and they're all wondering at some point or another, man, how long is it going to take to fill up? And the best part here, or one of the better parts, is that we don't get our answer from the answer key in the back of the teacher's edition. We instead just watch the end of the movie. And that's terrifying, all right? Because the theoretical models that always work out in the answer key, the back of the teacher's edition, like that's great, but it's scary to talk about sources of error when the theoretical does not match up with the practical. But those conversations have been so valuable, among the most valuable. I encourage math teachers I talk to use multimedia because it brings the real world into your classroom in high resolution and full color. To encourage student intuition for that level playing field, to ask the shortest question you possibly can and let those more specific questions come out in conversation. To let students build the problem, because Einstein said so. And to finally, in total, just be less helpful. Because the textbook is helping you in all the wrong ways. It's helping you, it's buying you out of your obligation for patient problem solving and math reasoning to be less helpful. And why this is an amazing time to be a math teacher right now is because we have the tools to create this high quality curriculum in our front pocket. It's ubiquitous and fairly cheap. And the tools to distribute it freely under open licenses has also never been cheaper or more ubiquitous.